Hello, welcome to the introductory video of data science. The audience in this class are mostly seniors trying to acquire some knowledge about data science and its applications. Prerequisites for this course is CS 111, 112, 205, and 206. We assume no machine learning or linear algebra knowledge, but we will teach you some of the fundamentals of those topics. We'll also introduce some important topics in statistics. And this course is more of a broad introduction to tools and methods for doing data science. Hype or real? Why data scientist is the most promising job of 2019? All indications are this is probably real, but most people are trying to understand what data science is still. So let's get started. Here's our lecture outline. And we'll talk about a definition. We'll start with the definition of data science. But before that, we'll look at what a data scientist might do in the job. So your boss might say that you need a new big data-driven system that replaces the traditional service. The reason is that we want to provide a more customized service to each client or group of clients. So the system also must be robust and reliable. The system must be efficient and fast. In other words, it uses proper amount of memory and proper amount of processing and must process things faster. The system must be scalable as the data increases. In other words, we don't want the system performance to be linear with the size of the data. Almost a constant relationship is important. The system must also honor privacy preferences of each user. Now, what we describe here is a lot of things, a lot of requirements. Obviously, one person will not be able to do all of these things correctly. But it shows you what a data scientist would do on the job. When you try to get a data science job, you might be asked some interview questions like this. Given an Excel or SQL database of 2 tables of data given with information, you can answer some questions such as how many minutes worth of videos on the average the publisher have. Seemingly in this case, you have to combine 2 sets of information using perhaps a common ID. So video ID may be the common ID here. We'll learn how to combine such things, and we will also learn SQL databases later in the course. Here's another question that asks a probability question, but this requires some level of understanding of Bayes' theorem, and we'll talk about those things as well. This question might be you're working for an app company, and the company wants to know how to introduce a share video feature, and how would you design this experiment, and how would you collect the data, and how do you know when you're successful? So data science is a combination of hacking skills, math and statistics knowledge, and substantive expertise in a field. But in this course, I assume no expertise in a field because you're all students and you haven't probably worked in the industry yet. So you can see some of the intersection between these things that are really important to be a data scientist. So essentially, data scientists need to learn machine learning, but machine learning is not data science. It's not the only thing about data science. And they also have to have some math and statistics knowledge and also some hacking skills to understand this. Data science is interdisciplinary, combining a number of fields from statistics, linear algebra, artificial intelligence, machine learning, database, and data warehousing. A definition of data science could be that an interdisciplinary field that applies data-centric computational and inferential thinking to solve problems of interest. A wave of data science can be looked at as it's trying to explain the past and predict the future. Explaining the past is by using the data that's already available. We can draw that data, we can plot that data, we can do all kinds of things. We'll learn some of those things in this class. And try to understand what this data is. And the data can come from categorical data or numerical data. Now the data, when we talk about data, data is not just a bunch of numbers, but they can be images, they can be video files, they can be sound, they can be text. So there's a lot of different types of data that exist in the world. And then we have to learn how to process this data as a unit. Predicting the future includes classification, modeling, regression, clustering, and so on. And we'll learn some of the techniques in this class about predicting the future. What's the difference between a data scientist and a computer scientist? If you think about traditional programming, so we will compare traditional programming to machine learning. Just as programming is not computer science, machine learning is not data science. In traditional programming, we will have data, and then we will write a program and feed that program and the data to a computer and get an output. An example would be something like find the square root of a number by approximation method. So we will program this algorithm into a computer. On the other hand, in machine learning, we have some data and we know what the expected output for that data, and we want machine to learn by looking at this data and what the possible outputs are. Then the machine provides us with a program, which is really a model of understanding new data and what the output for those data would be like. So for example, you can say, I got a bunch of data. I want to find the best curve that fits this data, which we call linear regression, and we can find this information. Now, so the computer science and data science can be combined. So essentially, we could take these programs that are generated here and feed them back into a computer, and we can begin to modify these things to make things faster and faster. So as a computer scientist learning data science, you have a bigger advantage of an already good understanding of mathematics and systems and algorithms behind computer science, and then using them to become a better data scientist. So a computational data scientist is what I think of computer scientist as a data scientist. So if you combine computer science and data science, you get this computational data science, where we study big data systems and big data algorithms, because the classical algorithms might not work for doing data science. And big data systems, classical ways of storing data on our computer might not work. We also have to look at the computational complexity and perhaps the correctness of programs and other things to make sure our systems are performing as expected. A computational data scientist need to develop computational thinking and inferential thinking. So computational thinking is abstraction. That means abstract away the details of complex systems. Modularity is design the systems that are easy to maintain. Scalability is systems need to support increased growth in data and network traffic. Robustness means the ability to overcome adverse effects that we haven't anticipated. In terms of inferential thinking, we want the machine learning to give us, is a form of statistical thinking. If you think about machine learning, which are based on decision trees and probabilistic models, but the problem in ML algorithms may not give an insight to the problem. So a data person, just without understanding of inferential thinking, may just start processing data without thinking about the content. So you need to learn how to develop methods to explain the underlying phenomena using data. For example, you can say the traffic seems to stop for no reason and collect the data to see why and explain it. Where the data science opportunities are, you can see that many of the data scientists' opportunities are in the lowest level that contains instrumentation, logging, sensors, user-generated content, and so on. And then at the top level, you have reliable data flow pipelines, structured and unstructured data storage. You got to clean the data, you got to analyze the data, you can create experimentation, and you can apply deep learning and AI things. So as a computer scientist, mostly you're going to be in the top 3 layers, which are going to be the highest paid opportunities in the industry, I assume. So here are some questions in data science, some broad questions. Are heights and weights increasing in the population in general? So how do we answer that question? Where should we put docking ports for our bikes? Do left-handed people have shorter lifespans than right-handers? What should we eat to avoid dying early of heart disease? And so on. We can ask a lot of questions such as those things. So let me skip through the course overview and let me get to the other part. So let's take a look at the data science life cycle. So in the data science life cycle, the first step is the data creation, but it's in a circle, it's a life cycle. You create the data, you process the data, you analyze the data, and then you have to find a way to preserve this data. And then you want to access this data in some way, and you want to reuse this data in some other way. And so you can have new data created all the time and added to this life cycle. So it's a continuous thing that will continue to update your model as the new data comes in. Another way to look at data science is to say, let's formulate a question or problem and acquire and clean the data to answer that question. Let's do some exploratory data analysis by looking at visualizations and draw conclusions and maybe go through this cycle a few times and then finally submit reports, decisions, and solutions. So the purpose of computing is insight, not numbers. So that's what's important in a data scientist. How do we interpret data when we see data? So in this case, note that we have used one scale for x-axis, the year, and two scales for y-axis on both sides. If you look at this graph seems to indicate that the use of chemicals in corn and soya is highly correlated to autism. Is this conclusive? We know that the population also increased during this period. Perhaps we should plot the population curve as well in this period. We can compute the rate of increase in population and see if it's the same rate as shown in this graph. So if the 6 to 21-year-old population also increased during the same period, can we conclude that something about this graph? So the key in this case is to standardize the scales to understand our data better. So this graph shows that the organic food sales also increase with autism. Does this mean organic foods are somehow responsible? In general, we tend to look at organic foods in a more positive way, but what if they contribute to the autism? How do we answer that question in the affirmative? So in some ways, these two graphs, what you saw, the last graph and this graph, are somewhat contradictory. So here's another case of bad correlation. This shows that people who died by falling out of their wheelchair correlates with cost of 16-ounce potato chips. Obviously, we have no reason to think that these two are correlated. But how can you say for sure? In this course, we'll be using a lot of tools for data science. So we'll be looking at TensorFlow for doing deep learning. And we'll look at the Spark for distributed computing, Jupyter Notebooks, and some scientific learning, Python. We're not going to study R and so on, but there are a lot of tools for doing data science. So the first thing you need to do is to install the Jupyter Notebooks. It's an open source application that allows you to create and share documents that contains live code equations and so on. You can install Jupyter Notebooks directly, or you can install them as part of Anaconda installation package. So this is the end of the first sort of introductory lecture. We'll talk more about things in detail next time.